Einstein, on Aether and Relativity. New Modern Translation 2025. Albert Einstein and Harry Yoon, Translator. Foreword by the translator Harry Yoon, Ph.D. This booklet contains the lecture given by Einstein at the Leiden University in the Netherlands in 1920. The main topic was the concept of ether related to relativity. But Einstein goes more broadly and much deeper in this lecture. The idea of space puzzled people for millennia. The first person who contemplated about space was the ancient Greek philosopher Anaximander of Miletus. He presumed that there existed something, possibly materialistic, which he called apeiron, that pervaded the entire universe. Everything came from apeiron, and everything would eventually go back to apeiron. The idea of void, or nothing, was first postulated by the so-called atomists like Leucippus and Democritus of Abdera. In the ancient Greek atomic theory, there were atoms in the background of void that made up matter. Plato then postulated the existence of ether, the fifth element, beyond water, air, earth, and fire, which permeated the heavenly world. Light, for example, the light from distant stars, propagated through the ether according to his theory. These classical concepts of space, ether, and void, etc. were well summarized by Aristotle in his book, Physics, meaning nature in Greek, in the 4th century BC. When Newton formulated his theory of mechanics in the 17th century, he postulated the existence of absolute space, which extended throughout the entire infinite universe. One thing to note from the outset is that the word space means very little, partly because, ironically, it means so many different things. To many people, space conjures up a meaning of nothing in which real things can be placed. In Newton's mechanics, however, space was something materialistic, just like Anaximander's apeiron or Plato's ether. Nothing cannot pervade the entire universe, obviously. In this lecture note, Einstein compares Newton's space with Maxwell's ether, which is rather interesting. Newton himself did not believe in the ether in the sense of Plato, and he thought that no light wave could propagate through a mechanical medium, which turned out to be true according to the current understanding, largely thanks to Einstein. The concepts of space and vacuum, broadly speaking, are not fully understood at this point. The confusion and mystery that existed at the time of ancient Greece still remain, despite the huge progress in our understanding of nature since that time, for the last 2 millennia or so. This article by Einstein, although it is based on the lecture given over 100 years ago, still includes a lot of hidden gems full of Einstein's insights. For anyone who is genuinely interested in understanding our universe, space and time or space-time are the most basic building blocks. For such people, this article is a must-read for inspiration if nothing else. Note that this is the only writing lecture by Einstein that is solely focused on the idea of ether in the context of relativity, both the special theory and the general theory of relativity. Ether and the Theory of Relativity by Albert Einstein. Prologue. Dear University trustees, professors, alumni, and students of this university. To all of you, ladies and gentlemen, I am truly honored by your presence today. The ether hypothesis. Alongside the idea of ponderable matter, which comes from the abstraction of everyday life, physicists have postulated the existence of another kind of matter, ether. How has this idea of ether come about? The origin of this idea can be probably traced to the following 2 factors. The phenomena which have given rise to the theory of action at a distance, and the properties of light which have led to the undulation or wave theory of light. Let us briefly consider these 2 subjects. Action at a distance. We do not seem to experience anything like action at a distance in real life, that is, unless you are a physicist. When we casually survey the experiences that we have with material bodies, it appears at first that there are no other interactions than those occurring through direct contact. This kind of forces are prevalent in our daily life, and they include, for example, transfer of motion through impact, action through pressure and tension, heating or starting combustion by a flame, and so on. In truth, gravity is indeed a force acting at a distance, in fact, even over a long distance, and it plays a major role in our everyday experience. However, since the weight of a body, which is due to gravity, appears to us as something which is constant in daily experience, and which is not tied to any noticeable cause and effect that is changing in time or in space, we do not usually think of gravity causing weight in everyday life. We do not, therefore, generally notice its character as action at a distance. It was only through Newton's theory of gravitation that a cause for gravity was first put forward. In this theory, the gravity was interpreted as a force acting at a distance which was coming from masses. Newton's theory probably represents the greatest step ever taken in our pursuit to understand the essential, causal relationship between natural phenomena. And yet, this theory still caused a great deal of apprehension and discomfort among Newton's contemporaries. This was due to the fact that Newton's theory appeared to be in contradiction with the fundamental principle, arising from our other more prevalent experience, that there could only be mutual interaction through actual contact, and not through an unmediated action at a distance. The birth of ether. The human pursuit of knowledge can only endure such a sharply contrasted dualism with a great reluctance, if ever. How could one save the unity of the conception of the forces of nature? One way to achieve this would be by trying to view the forces which we perceive as contact forces also as the same kind of forces acting at a distance in fact. But such a character should be only noticeable at a very short distance for these contact forces. This was the path which was mostly preferred by Newton's followers, who were completely under the spell of his doctrine. Alternatively, another way to do it would be by assuming that the Newton's gravitational forces only appear to be actions at a distance, but they are, in reality, transmitted through a medium that permeates space, that is, either through the motions of this medium or through its elastic deformation. Thus, the quest to unify our conception of the nature of forces led to the hypothesis of the existence of an ether. However, this second idea did not initially bring any progress to the theory of gravitation or to physics in general. Hence, people just ended up treating Newton's law of the gravitational force as an axiom that could not be further reduced. The ether hypothesis, however, always had to play a role in the thinkings of physicists, even if at first it was only a dormant role. The wave theory of light. When, in the first half of the 19th century, the far-reaching similarities between the properties of light and those of the mechanical waves in ponderable media became apparent, the ether hypothesis gained a new support. It seemed beyond doubt that light must be interpreted as an oscillation process in an elastic but otherwise inert medium that filled space. It also seemed to necessarily follow, from the polarizability of light, that this medium, i.e., the ether, must be of the nature of a solid body, because transverse waves are only possible in such a solid-state medium but not in a fluid. The theory of the stationary, luminiferous ether. Based on this consideration, one was naturally led to the theory of the quasi-solid luminiferous ether made of the constituent parts that were only partially movable relative to each other. It was supposed that these constituent parts were not able to carry out any other motions than the small deformation motions which corresponded to the propagation of light waves. This theory, called the theory of the stationary luminiferous ether, subsequently found a crucial support in the experiment of Fizeau, which was also fundamental in the development of the special theory of relativity. Based on the experiment of Fizeau, it had to be concluded that the luminiferous ether did not participate in the motions of ponderable bodies. The phenomenon of the stellar aberration also provided a strong support in favor of the theory of this quasi-rigid and quasi-solid state ether. Maxwell's theory of electrodynamics. The development of the classical theory of electrodynamics, along the path that was taken by Maxwell and Lorentz, brought about a very peculiar and unexpected twist in the development of our ideas about the ether. For Maxwell himself, The ether was still a structure with purely mechanical properties, but with the mechanical properties of a much more complicated nature than those of ordinary material solid bodies. Ultimately, however, neither Maxwell nor the people after him succeeded in devising a comprehensive mechanical model of the ether that would have provided a satisfactory mechanical interpretation of Maxwell's laws of the electromagnetic field. The laws were indeed clear and simple, but their mechanical interpretations were unwieldy and even self-contradictory. Dualism, mechanics and electrodynamics. Little by little, almost under the radar, theoretical physicists slowly and reluctantly adapted to this situation, influenced especially by the electrodynamic investigations of Heinrich Hertz. This situation was, however, not ideal from the point of view of their mechanical world program. They had previously required that a final theory of electrodynamics should be solely based on the fundamental concepts that belonged exclusively to mechanics, e.g., mass densities, velocities, deformations, pressure forces. But they gradually became accustomed to accepting electric and magnetic fields as fundamental concepts alongside the fundamental concepts of mechanics, without requiring mechanical interpretations for them anymore. Thus, the purely mechanical view of nature had been gradually abandoned. This shift in our view, however, ended up creating a dualism in the foundations of physics, which was unacceptable in the long run. In order to solve this problem, attempts were made in the reverse direction as well, that is, to explain the fundamental concepts and principles of mechanics from those of electromagnetism. It appeared that these efforts were justified, especially since our confidence in the strict validity of Newton's equations of mechanics seemed to have been shaken by the recent experiments on beta rays and high-speed cathode rays. Hertz's theory of ether. In Heinrich Hertz's theory of ether, the dualism mentioned above still remains, largely unmitigated. In his theory, matter acts not only as a carrier of velocities, kinetic energy, and mechanical pressure forces, but it also acts as a carrier of electromagnetic fields. Since such fields also occur in a vacuum, i.e., in the ether free of matter, the ether also appears to be acting as a carrier of electromagnetic fields. The ether seems to be entirely similar and subordinate to ordinary ponderable matter. It participates in the motions of matter, and hence it has a velocity everywhere in empty space, in such a way that the velocity of the ether is continuously distributed throughout the entire space, at every point. Hertz's ether is not different in any fundamental way from ponderable matter, which also exists partly in the ether. Hence, Hertz's theory suffered not only from the defect that it attributed mechanical states to matter and the ether on the one hand, and it also attributed electromechanical states to both of them on the other hand, which have no relationship with each other at the conceptual level. But it was also in contradiction with the result of Fizeau's important experiment on the speed of the propagation of light in moving fluids, as well as other generally accepted facts of experience. Lorentz's theory of ether. Such was the state of things when H.A. Lorentz got involved. He brought theory in line with experience through a great simplification of the theoretical foundations. He achieved this most important advance in the theory of electrodynamics since Maxwell by taking away almost all mechanical properties from the ether and likewise all electromagnetic properties from matter. Not only in empty space, but also in the interior of material bodies, it was the ether that was the sole bearer of the electromagnetic fields, and not the matter conceived as atoms. According to Lorentz, only the elementary particles of matter are capable of carrying out motions, and their electromagnetic affinity lies solely in the fact that they carry electric charges. In this way, Lorentz succeeded in reducing all electromagnetic phenomena to Maxwell's field equations in empty space. As for the mechanical nature of the Lorentz's ether, therefore, one can say, somewhat comically, that immobility is the only mobile property that H.A. Lorentz left it with. It may be added that the entire change that the special theory of relativity brought about in the conception of the ether consisted in one single fact. That is, it took away from the ether its last mechanical trait, namely the very immobility which was left by Lorentz. How this is to be understood will be explained next. The special theory of relativity. For the development of the space-time theory and kinematics of the special theory of relativity, the Maxwell-Lorentz theory of the electromagnetic field served as a model. The Maxwell-Lorentz theory therefore satisfies the conditions of the special theory of relativity. But in addition, when it is considered from the viewpoint of special relativity, it acquires a novel perspective. Suppose that K is a frame of reference with respect to which Lorentz's ether is at rest. Then the Maxwell-Lorentz equations are initially valid with respect to K, and only with respect to K, according to the special theory of relativity. However, the same equations should apply in the exactly same form with respect to any new frame of reference K', which is in uniform translational motion relative to K. Then arises the following uncomfortable question. If the frames of reference K and K' are physically completely equivalent, then why should I distinguish K over K' in a theory by assuming that the ether is stationary relative to K? For the theoretical physicist, such an asymmetry of the theoretical structure is intolerable, which does not correspond to an asymmetry of the system of experience. The physical equivalence of K and K', while assuming that the ether is at rest relative to K, but it is in motion relative to K', does not seem exactly incorrect to me from a purely logical point of view, but it is nevertheless unacceptable. The demise of ether. It appeared that the most obvious view that could be taken in this situation would be the following. The ether does not exist at all. The electromagnetic fields are not states of a medium, but they are independent physical entities which cannot be traced back to anything else, and which are not bound to any carrier, just like the atoms of ponderable matter. This view made all the more sense because, according to Lorentz's theory, electromagnetic wave carried momentum and energy like ponderable matter, and because, according to special relativity, both matter and electromagnetic wave were just special forms of distributed energy, with ponderable mass losing its special status and appearing only as a particular form of energy. The resurrection of ether. However, a closer examination reveals that this denial of ether is not necessarily required by the special theory of relativity. One can assume the existence of an ether. Only one must refrain from ascribing to it a definite state of motion. That is, one must take away from it, by abstraction, the last mechanical characteristic which Lorentz left to it. Later, we will see that conception of this kind of viewpoint is intellectually justified by the results of the general theory of relativity. For now, I will try to make the idea more concrete, relying on a somewhat lame comparison. Imagine waves on the surface of water. This process can be described in two entirely different ways. First, you can follow how the oscillatory interface between water and air changes over time. But alternatively, you can also follow, perhaps with the help of small floating bodies, how the positions of the individual water particles change over time. If there were no such floating bodies for tracking the motion of the particles of liquids, and if nothing else was noticeable in the whole process other than the changing position of the space occupied by water over time, then we would have no reason to suppose that water consists of moving particles. But nonetheless, we can still characterize it as a medium. Something similar exists in physics, that is, with regards to the electromagnetic field. One can think of the field as consisting of lines of force. If one wants to interpret these lines of force as something material in the usual sense, one is tempted to interpret the dynamic processes as the processes of motions of these lines of force, in such a way that each individual line of force is tracked through time. It is well known, however, that such a way of looking at the electromagnetic fields leads to contradictions. The non-mechanical ether. We have to say in general that it is possible to imagine extended physical objects to which the concept of motion cannot be applied. They must not be thought of as consisting of particles that can be tracked individually through time. In Minkowski's formalism, this is expressed as follows. Not every extended structure in the four-dimensional world can be understood as composed of world lines. According to the special theory of relativity, the ether cannot be assumed to be consisting of particles that can be traced in the course of time. But the ether hypothesis itself does not contradict the special principle of relativity. We just have to be careful not to ascribe a state of motion to the ether. At first, from the standpoint of the special theory of relativity, the ether hypothesis appears to be a pointless hypothesis. In the electromagnetic field equations, apart from the electric charge densities, only the field strengths appear. The time evolution of electromagnetic processes in a vacuum seems to be completely determined through the internal interactions governed by these equations, uninfluenced by other physical quantities. The electromagnetic fields appear as ultimate realities that cannot be reduced any further. And hence, at first sight, it seems superfluous to postulate a homogeneous and isotropic etheric medium whose states are to be understood as those fields. On the other hand, however, a strong argument can be made in favor of the ether hypothesis. Denying the ether ultimately means that we are assuming that empty space has no physical properties at all. The fundamental facts of mechanics are not in harmony with this view. The mechanical behavior of a physical system floating freely in empty space depends not only on the relative positions, distances, and relative velocities, but it also depends on its state of rotation, which physically cannot be attributed as a characteristic of the system itself. As for Newton, in order to be able to view the rotation of the system as something real, at least formally, he treated space as a physical object. Because he counts his absolute space among the real things, the rotation relative to an absolute space is also something real for him. Newton might just as well have called his absolute space ether. The only essential thing is that, in addition to the observable objects, we have to regard another, possibly imperceptible thing as real, in order to be able to view acceleration or rotation as something real. Mach's principle. It is true that Mach tried to avoid the necessity of assuming something unobservable real by attempting to introduce into mechanics the concept of a mean acceleration relative to the totality of the masses in the universe, instead of an acceleration relative to an absolute space. But an inertial resistance to an acceleration relative to distant masses presupposes an unmediated instant action at a distance. Since the modern physicist does not believe that such an action is possible, he also ends up once again with this view of the ether, which has to serve as a medium to mediate the effects of inertia. This concept of the ether that Mach's approach leads to is, however, fundamentally different from the concept of the ether used by Newton, Fresnel, and H.A. Lorentz. Mach's ether not only determines the behavior of the inertial masses, but its state is also determined in turn by the inertial masses. The ether of general relativity. A full realization of Mach's idea is found in the ether of the general theory of relativity. According to this theory, the metric properties of the space-time continuum can be different in the vicinity of different space-time points, and these metric properties are determined, at least partly, by the matter that is present around the region under consideration. At long last, the view that space is physically empty has probably been eliminated thanks to the realization that the relationships between unit measuring sticks and clocks are variable over space and time, or in other words, empty space is neither homogeneous nor isotropic in physical terms. Incidentally, this realization forces us to describe its physical state using 10 functions, the gravitational potential fields, g mu nu. This means that the concept of ether has once again acquired a clear physical meaning, albeit far different from that of the ether of the mechanical wave theory of light. The ether of the general theory of relativity is a non-mechanical medium, which is itself devoid of all dynamical and kinematical properties, but which nonetheless participates in determining mechanical and electromagnetic events. The spacetime fields of general relativity. The fundamental novelty of the ether of the general theory of relativity, compared to Lorentz's ether, lies in the following fact. The state of the ether of general relativity is determined at every point according to a law, in the form of differential equations, which specifies its relationship with matter and the states of the ether in neighboring points. On the other hand, the state of Lorentz's ether in the absence of electromagnetic fields is not controlled by anything else outside itself, and it is the same everywhere. The ether of general relativity, with the metric functions which describe its space-time variations, can be conceptually transformed into Lorentz's ether by setting these metric functions constant, while disregarding the causes which determine its state. Therefore, one may as well say that the ether of the general theory of relativity has emerged from the ether of Lorentz through relativization, as in to relativize. Open questions regarding the ether of GR. As for the role that this new ether is destined to play in the physical world view of the future, we are not yet entirely clear. We know that it determines the metric relations in the space-time continuum, e.g., the relative positioning possibilities of solid bodies and the gravitational fields. But we do not know yet whether it plays an essential role in the structure of the elementary particles of electromagnetic nature that constitute matter. We also do not know whether its structure deviates from the Lorentzian structure significantly only in the vicinity of ponderable masses, or whether the geometry of spaces in the large cosmic scale is otherwise more or less Euclidean. However, based on the gravitational field equations of general relativity, we can assert that non-zero deviation from the Euclidean behavior must exist in spaces of cosmic magnitude if the mean density of matter in the universe is positive, no matter how small it may be. If that is the case, then the universe must necessarily be spatially closed, and it should be of finite size, with its size to be determined by the value of that mean density. Two realities, spacetime and matter. If we consider the gravitational field and the electromagnetic field from the standpoint of the ether hypothesis, there is a remarkable difference between the two at the fundamental level. No space, not even part of it, can exist without gravitational fields, since they provide space with its metric properties. Without them, space wouldn't even be imaginable. Therefore, the existence of the gravitational field is inseparably connected to the existence of space. On the other hand, a part of space can very well be thought of without the existence of any electromagnetic field. In contrast to the gravitational field, the electromagnetic field thus seems to be related to the ether only indirectly, if any. That is to say, as of yet, the formal nature of the electromagnetic field is no way determined by that of the gravitational ether. According to the present state of the theory, it looks as though the electromagnetic field rests on an entirely novel formal theoretical structure, in a sharp contrast with the gravitational field. It is as if nature could just as well have equipped the gravitational ether with fields of a completely different type, e.g., with fields of a scalar potential, instead of fields of the electromagnetic type. Since, according to our current understanding, the elementary particles of matter are, in their essence, nothing more than condensations of the electromagnetic field, our world view at the present moment recognizes the two conceptually completely separate realities, although incidentally linked to each other, namely, gravitational ether and electromagnetic field, or as they could also be called, space and matter. Unification of space-time and matter. Of course, it would be a great step forward if it were possible for us to find a way to conceive the gravitational field and the electromagnetic field together as one unified entity. Only then would the era of theoretical physics, founded by Faraday and Maxwell, come to a satisfactory ending. The disparity between ether and matter would then fade away, and the whole of physics would become a self-consistent system of thought, just like geometry, kinematics, and the theory of gravitation according to the general theory of relativity. An extremely ingenious attempt has been made in this direction by the mathematician Hermann Weyl, although I do not believe that his theory will ultimately stand up to reality. Furthermore, when thinking about the immediate future of theoretical physics, we should not automatically reject the possibility that the consequences derived from quantum theory could set insurmountable limits to field theory. Conclusion. In summary, according to the general theory of relativity, space is endowed with physical qualities. In this sense, therefore, we can say that ether exists. In the framework of general relativity, space without ether is unimaginable. In such space, there would be no propagation of light. Furthermore, there would not even be a possibility of the existence of measuring sticks and clocks, and hence there would be no existence of spatio-temporal distances in the sense of physics. However, this ether of general relativity should not be thought of as endowed with the characteristic property of ponderable media, that is, consisting of parts that can be tracked through time. The concept of motion should not be applied to it. Afterword by the translator Harry Yoon, Ph.D. One of the most fascinating things about the universe that we live in is the fact that it appears to consist of two components, namely space-time and matter. This idea was ultimately born in ancient Greece, as we briefly mentioned in the introduction. Interestingly, even the ancient philosophers seem to have made a distinction, albeit vaguely, between space and empty space or void. That is, space was real or physical, whereas void was not. Time was generally considered separate from space, pretty much until the advent of special relativity. As Einstein points out in this article, Newton also considered space a physical entity, and not an empty space. Clearly, this was a prevalent view, with some minor variations, for over 2 millennia, pretty much to the time of Maxwell and Lorentz, if we use the terms like space and ether more or less equivalently. Philosophers like Descartes and Leibniz were a minority, in that they didn't believe in the existence of space. Leibniz, for example, space was sort of an emerging concept based on the relationship between material bodies. As far as relativity is concerned, Einstein initially thought that space, or ether, was unnecessary while he was working on special relativity. In fact, the mechanical ether of Maxwell and Lorentz was not consistent with the principle of relativity. Hence, upon the birth of the special theory of relativity, ether was considered all but dead. Then, as Einstein started working on his general theory of relativity, he immediately realized that he needed something physical. Now, according to the general relativity, space or spacetime is a physical entity, in fact, the gravitational field, but without any mechanical properties like motion. As Einstein explains in this article, it was also retroactively realized that the existence of space ether was not incompatible with special relativity after all. Therefore, we can still assume that flat space exists even without matter, which creates the gravitational field and hence space in general relativity. This is the current view of space, spacetime, according to relativity. There has been absolutely no further progress in our understanding of space and time since the time of Einstein. On the other hand, when it comes to matter, we have made an enormous progress, especially for the last 100 years or so. The Standard Model of particle physics, for instance, is one of the most complete theories in our scientific history. One interesting thing to note is that quantum field theory, which is at the foundation of modern particle physics, predicts the phenomenon known as the vacuum fluctuation. At this point, however, we do not have a full understanding of this phenomenon. Nor do we fully understand the relationship between the spacetime of general relativity and the quantum vacuum. Hence, this dualism of spacetime and matter still remains at this point, after over 2,000 years of our scientific quest. The Einstein's Books Project. We are working on new translations of some of the more important writings of Einstein into English, using more modern terminologies. Your purchase of this book supports our effort. Einstein's Relativity, 1916. Learn relativity from Einstein's book, Einstein's Relativity, the Special Theory and the General Theory. This book is not available on Amazon.